Okay, so how's everybody doing? Okay? Okay, so let's get started. So chapter 1 of Rudin is dealing with the numbers. In particular, it's dealing with the real numbers, right? Which is something you probably never thought about. But maybe you didn't think about too carefully. Basically, what's dealt with in chapter 1 is, what does R have that Q doesn't have? Okay, maybe I'm not sure if you're familiar with this notation. This is the real numbers. R stands for the real numbers. Q stands for the rational numbers. There's something called the Bourbaki notation. Bourbaki notation. So N stands for the natural numbers. So natural numbers. Z for the integers. Q for the rationals. R for the reals. And C for the complex numbers. So anyway, have you all seen this before? Yes, some of you, maybe most of you. Okay. Okay. So what does R have that Q doesn't have? Okay. That's really the question that we will answer in this first chapter. We're going to start off. With Q, and the first thing we're going to notice is that Q has some problems. Okay, so there are problems. Problems with the rational numbers. Right? Q stands for quotient, right? So you're taking quotients. The rational numbers are, of course, quotients of integers, right? You're taking one integer over another. That's why it's called Q. Okay, so Q has some problems. First one is called algebraic incompleteness. Algebraic incompleteness. Okay, and this is kind of a difficult problem, and the problem is that you can make equations using Q that have no solutions in Q. Okay, so like for a simple one, x squared minus 2 equals 0. Right? All the coefficients here are rational coefficients, right? But there's no rational solution to this, right? There's no rational number whose square equals 2. Okay, so this is called algebraic incompleteness. Okay, the one that will be more relevant to us is just called incompleteness. And if you wanted to distinguish it, maybe you would call it sort of analytic incompleteness. But analytic incompleteness is a little bit harder to describe, but it's basically the fact that there are holes. There are holes in Q. Okay, that is, you can have a sequence of numbers like 1, 1.4, 1.41, 1.414, 1.4142, blah blah blah. So this is the beginning of the square root of 2, and if you truncate these the square root of 2 with increasing fineness, you can get this sequence that tends towards the square root of 2. Right? These numbers are tending towards something. They're getting closer and closer to something, but that something doesn't exist. Right? What I mean is that these numbers are all rational numbers. Right? These are all rational numbers, right? But the thing that they tend to doesn't exist in the rational numbers. Right? So you have if you were in some sort of rational world, right? You say, oh, I've got one, I've got 1.4, I've got 1.41, I've got 1.414, et cetera, et cetera. But then there's this hole there. These things are getting, the distance between them is getting smaller and smaller, but the thing that they approach, their limit, there's a hole there, okay? So this idea of getting closer to something and the idea, we'll have to make this is kind of hand wavy, so this is not really precise thinking, but this is the idea that there are holes in Q. Okay. So okay. So and this actually has some historical historical interest. As you may know, the Pythagoreans, 2,500 years ago, the Pythagoreans used a rational number system. And so, they believed that the world was basically sort of based on rational numbers, and that, because of, various phenomena like musical phenomena and stuff, they believed that the whole world was based on this sort of like ratios and things, and that the universe had this music to it, based on rational numbers. But one thing that bothered them was what happens if you take a right isosceles triangle? If the world is based on rational numbers, what rational number is this, right? What rational number is this? And of course, this is not a rational number, right? It's the square root of 2. Eventually, the story goes, and it's probably not a true story, but the story goes that one of the Pythagoreans, discovered that this thing could not be described as a rational number, and the story is that they threw him off the boat immediately because they just killed him immediately. Okay. In any case, the argument that he gave, I'm not sure if it was this one, but here's an argument that shows that that the square root of 2 is irrational. Okay. So, and I'm sure you probably read it already. Claim x squared equals 2 has no solution in the rational numbers. Okay. Okay. So the proof is the so-called proof by contradiction. So how many of you have seen proof by contradiction before? Anybody? Close your eyes for a second. Okay. Raise your finger if you haven't seen proof by contradiction before. Okay, open your eyes, please. Okay, great. I don't need to explain it. Okay, so it's proof by contradiction. So we'll start by, do by contradiction. Right. Suppose that there is a rational solution. Okay. Suppose there is a rational solution. So in other words, so there is some, i.e., some rational number p over q, right, in the rational numbers, such that p over q squared equals 2. Everybody okay so far? Okay. Suppose there's some rational solution, right? Some rational number whose square equals 2. Notice that we can assume that there are no common factors. There are no common factors between p and q, right? Because if p were like k a and then q were kb, we could just cancel out. We could just cancel out the k's, right? So we cancel out any common factors. We assume we can assume without loss of generality is normally abbreviated like this. Without loss of generality, you can assume that they have no common factors. Okay. Okay. So so we'll start from there, and we'll see if we can get to a contradiction. Okay. So you say, okay, well, if p squared over q squared equals 2, then p squared equals 2q squared, right? So we're just going to make deductions. So the typical proof by contradiction, you start from the thing, you start by assuming the opposite of what you're trying to prove, and then make deductions until you reach a logical contradiction, right? So and then that shows that the thing that you assumed had to have been false, right? Which means that your initial statement was true. Okay. Okay. So I guess you probably read this in the text. So what do we do next? P squared equals 2q squared. Where can you go from there? Anybody remember?
Even.
So
P squared is even.
P squared is even, right? So P squared is even, right? Because P squared is twice something, right? So it's an even number, and that implies that P is even, right? Why is that true? So that actually requires a little bit of proof. Let me be careful at the beginning. So why is it true that why does p squared even imply p even? Okay. One way of doing it is to take the contrapositive statement. I don't know. In logic, you can have a statement A implies B. Okay, and then there's something called the contrapositive statement, which is that not B implies not A. Okay, and so if you want to prove these statements, A implies B and not B implies not A, are logically equivalent. And so if you want to prove this, it suffices to prove this. Okay, they're basically the same statement, but sometimes it's easier to attack the contrapositive. Okay, so in this case, what's the contrapositive statement? The contrapositive statement would be p odd implies p squared odd. Does that make sense? Right. So prove the contrapositive is p odd implies p squared odd, right? P odd. So, and that's actually a little bit easier to do, because you say, well, look, so which is true because if p is odd, then p is some even number p is some even number plus 1, right? Right? If p is odd, p odd means that p is some even number plus 1, right? And then p squared is going to be 4m squared plus 4m plus 1, right? Right? Which is an even number plus 1, right? Which is odd. Which is odd. Okay, so we proved the contrapositive statement, and so p squared even implies that p is even. Okay, is that all right with people? Okay. Okay, so this this needed to be proven. Okay, everybody okay so far? Okay, so so right now we have that P must if this is true, then P must be even, right? Which means that P equals like 2k for some integer k, right? Okay, where do we go from there? Go ahead, Anne.
Could we square P and say that Q is then even?
Yeah, exactly. So in that case, we have that 2k squared equals 2q squared, right? So from, let's call this double star. So using double star implies that p squared equals 2q squared, right? Which means that 4k squared equals 2q squared. But that means that q squared equals 2k squared. Right? So just divide both sides by 2. Right? So what does that tell you? Q is also even, right? Because that tells you that q squared is even, and just as we said before, the square of the number being even implies that the number itself must be even, right? So that tells you, as before, q must be even. Okay, but that's a contradiction. That's a contradiction because we assumed at the beginning that p and q had no common factors, right? P and q were supposed to have no common factors, but p is even and q is even, so they have a common factor of 2, right? So, what we're saying is that if there were a rational solution, we could assume that they have no common factors, but they also have common factors, right? So having a rational solution leads to sort of logical craziness. Okay. So we reach this. I don't know if you've seen the symbol before. This means contradiction. So that's the end of the proof. Okay. Contradiction. Yeah, maybe if you're writing out, you should spell it out a little bit more, right? You'd say, contradiction because p and q were not supposed to have any common factors, and yet they're both even. Contradiction. Okay. Everybody okay? Okay, great. So so this is the famous proof from 2,500 years ago, supposedly, that got this person killed and destroyed the idea that lengths and rational numbers could be sort of placed in a one-to-one correspondence. Okay, there were lengths. It turns out there are lengths that are not rational. Okay. Many years ago, there was a cartoon called Reign the Conqueror about Alexander the Great. And the whole time there was this cult of Pythagoreans who were trying to stop something from happening. And if I understood the cartoon correctly, what they were trying to stop was the introduction of irrational numbers. Like the whole cartoon was about that, but sort of secretly. They didn't make that so clear. They were trying to stop something from coming into existence, and it had some sort of spooky name to it. But what it was the coming of the irrational numbers. Okay. 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 See, I'm missing a page. I'll be back in a minute. Sorry.
the date is?
So 19.
I thought it was the 20th.
Okay. Okay, so okay, so the next thing we're going to do is something that will seem a little bit obscure for right now, but the purpose of it will become clear shortly. Okay, so so this is going to be a little bit strange, but here's the claim. We're going to introduce two sets. The first one is a set of rational numbers where they are all they're positive and their square is less than 2. And the second is the set of rational numbers where again they are positive but their square is greater than 2. Okay, so you know, we who live in the real lived in real numbers, but let's pretend that this is the rational line, not the real line. Okay, so there's this hole here where there's this thing whose square is equal to 2, and you know, A is all the rational numbers that are here, and B is all the rational numbers past that hole. Okay, so there's this hole here. Okay, and then the claim is that so let these things be defined as such. Then A contains no largest number. And B no smallest. Okay. So A contains no largest number, B no smallest. So okay, I don't know how you feel about it, but you should be sort of like, what, you know, why are we doing this? Yeah, don't worry, that feeling will pass soon. Okay, so in any case, we want to show that A contains no largest number. In other words, whenever we take a number within A, there's always something bigger than it. Okay, there's always some number within A that's larger than that chosen number. Okay, so proof. So and we'll prove this first one. The second statement is proven in a very similar manner. Okay. So here's the idea. So here's Rudin's proof. So it says, well, let P be in A. Right. We want to show that you can always find something bigger that's still in A. Right. We want to show that there exists a Q in A such that Q is bigger than P. Okay. Is everybody okay with the backwards E? Backwards E, yeah, just meaning there exists, right? There exists another point within A with the property that Q is bigger than P. Okay, such that, right? Such that, right? So old-fashioned English, nobody says such that anymore except mathematicians. So we want to show this, okay? So Rudin basically pulls this number out of a hat. He says, Q is going to, let Q be P minus P squared minus 2 over P plus 2. Okay? So it says, I'm just going to pull this number out of somewhere, and then an easy calculation shows that Q squared minus 2 equals 2 P squared minus 2 over quantity P plus 2 squared. Okay, so you can, this is just arithmetic, right? You square it, subtract 2, and then reduce it, and you get this thing over here. Okay, I'm not gonna bore you with that. Okay, so he says, well, you know, pull this number out of nowhere, and then look at Q squared minus 2. Okay, well, P is in A, right? So P being in A means that, so now P being in A means that P squared minus 2 is negative, right? Because we're on the left side of the whole, right? So P squared minus 2 is negative, and so that tells us that this thing on the right side here is negative, right? So Q minus 2, Q squared minus 2 is negative. In other words, Q squared is smaller than 2, right? Right, so what you get is that this thing is negative, right? So Q squared is going to be less than 2, right? Q squared minus 2 is less than 0, right? Q squared minus 2 is less than 0, so Q squared is less than 2. Yes? Okay. Okay. So yeah, so Q squared, so from above, that implies that Q squared is less than 2, right? Which means that Q is in A, right? So Q is in A. So that's good. We've got this. We've got a rational number that lies within A, right? And what we also wanted was that number is going to be bigger than P, right? But you say, well, look, is Q bigger than P? Anybody see how that goes? By looking here? Why is Q bigger than P?
Minus P, and then because the numerator is negative.
The numerator is negative, exactly. The P squared minus 2 is negative. This is positive, right? So we're subtracting a negative number from P. In other words, we're getting bigger than P, right? Q is P minus a negative number. In other words, Q is P plus a positive number. So Q is bigger than P. Yes. So yes. Okay. Right. Negative P squared minus 2 over P plus 2 is positive. Okay. So that shows you that, so we've constructed, so Q is in A and Q is bigger than P, right? So in other words, no matter what P you choose in A, there's always another element of A that's bigger than you. Okay. Okay. So so what do you think about that? How do you feel?
You feel like an infinite list of numbers.
I'm sorry?
You feel like A is like an infinite list of numbers.
There's an infinite list of numbers?
Yeah.
Yeah. So like, you could then take Q and then take another, you could iterate this and then get another number that's closer and another that's closer. and that's closer, et cetera, et cetera. Yeah, you could get like some sort of infinite list of numbers. But I guess I was wondering how you felt about like pulling this number out of nowhere. Yeah. Okay. So I'm gonna prove it again in a different way, just for amusement. No, not for amusement, for sound pedagogical reasons. Okay. So the thing is that Rudin did not. So let me write it up again. So P in A, P in A, let Q be P minus P squared minus 2 over P plus 2. Okay, so I'm gonna write it up in a different way. So like I was starting to say, Rudin actually intended his book to be sort of like a bunch of cryptic notes, I think, that he would decipher for the class. So he would take his notes and then explain what was really going on. So part of the game of reading Rudin is trying to figure out what is really going on here. Okay, so like anytime you see something that is like unnatural, like where did that come from? Try to figure out why it's natural. Okay, let's try to figure out why it's natural. And okay, so here's the idea. So here is the square root of 2. Here is p, right? Here is 0, and you're trying to find a rational number that's between here and here. Okay. Okay. You want to find a rational number that's to the right of here, to the right of p. Okay. So here's what you do. Here's what you start off. You say, well, the first thing I'm going to do is I'm going to add on the square root of 2 minus p. Okay. That seems like a weird thing to do, but that's what I'm going to do. So I'm going to say, let's look at the distance here. The distance here is the square root of 2 minus p, right? That's the distance. So if we add that thing on, we get something that's to the right of p. But the trouble is that it's not rational, right? It's not rational, and it's not smaller than the square root of 2. Okay. So then you think, okay, well, how am I going to fix this up? I'm going to fix it up so that it is rational. So I'm going to do something from childhood. I'm going to multiply by the square root of 2 plus p, because I know that will give me 2 minus p squared, right? So that would make it rational, but in order to that might be too far out, right? That might be too far out, and so what I do is I want to multiply this length. So here's the idea. I want to multiply this length by a factor that changes the whole product into a rational number, but this factor that I multiply should be smaller than 1, right? I want this factor to be smaller than 1 so that I get, I take this length and I shrink it a little bit. I shrink it a little bit and I shrink it into a rational number. Okay, so here's the thing that's going to change it into a rational number. I want this factor to be smaller than 1. Well, p plus the square root of 2 is smaller than p plus 2, right? Because the square root of 2 is smaller than 2, right? So this is the factor I'm going to use, right? This is the factor I'm going to use. So I multiply it. I take my p and then I add on I add on this length, but multiplied by a factor that rationalizes it, and so that this factor is smaller than 1, so that I'm still underneath the whole. So I'm still to the left of the whole, right? And we see what that turns out into. That's 2 minus p squared over p plus 2, right? So that's what I'm adding on, right? For which Rudin perversely wrote as p minus p squared minus 2 over p plus 2. Okay, but if you decode it, I think if you want to make things really clear, you wouldn't write it in this way. You would write it in this way. You'd say, let q be p plus square root of 2 minus p times square root of 2 plus p over p plus 2. Okay, okay, so yeah. So you have to sort of unsimplify. There's some simplification that goes on here to make it look neater, but that hides what's the thought process that's going on. Okay, so kind of a challenge for all of us is to, whenever you see something, figure out, what's the real expression underneath it. For example, the area of a circle being pi r squared would probably be better written as pi r times r. If you think about how people figure out the formula for the area of if you look at how you actually figure out the formula for the area of a circle, then this is actually the right way to think about it. It's pi r times r, not pi r squared. Okay. Okay. So I hope that makes things a little bit clearer, right? Because if you think about it this way, then it's completely obvious, right? You don't have to go through the argument here. You just say, well, look, I'm taking the length from here, and then I'm multiplying by a factor smaller than 1. So now it's on the left of the whole, and I've chosen the factor so that the product is rational. Okay. Yeah. So always be asking yourself, why is this obvious? Why is this obvious? Okay, that's I think many of you are just sort of starting out in your theoretical math careers. This is something I think this is a good habit to keep. Just think, why is this the natural thing to do? Why is this the natural thing to do? Okay. 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 So temporarily, we're going to leave the world of numbers and enter the world of sets. Okay. So I'm hoping that all of you are familiar with the standard set notation, right? Like, let A be a set. You know what this stands for? What is this? Empty set, right? This is the empty set, right? Set with no elements. Set with no elements, right? You know what this means, right? This means X is an element of A, right? This means X is not an element of A, right? X is not an element of A. You know what this sort of thing means? What does this mean?
Subset.
Subset. A is a subset of B, right? In other words, if X is in A, then X is in B, right? Anything that is in A must be in B, right? In other words, A is contained in B, right? Any element of A must be also an element of B, right? And if I wrote A, superset B, then that would mean the opposite, right? That A, X in B implies that X is in A, right? If I write A equals B, that means that A contains B, and also A is A is contained in B, and A also contains B, right? A is both a subset and a superset. In other words, an element of A is always an element of B, and an element of B is always an element of A, right? So this goes both ways. X in A implies X is in B, and X is in B implies X is in A, right? So standard set notation. I hope you see that before. When do you see this these days? Like, when do you encounter this in your education? Do you encounter this in
Discrete math. I took discrete math.
discrete math?
Yeah.
It's not in middle school?
Oh.
You don't see it in K through 12 education?
Not really.
Wow, okay, things have changed. Because that was part of the K through 12 education, 40 years ago, 50 years ago. Yeah, set notation and stuff was kind of standard back then. Okay, interesting. Sad, but okay. Okay, so set notation. I guess I shouldn't be so reckless. Everybody okay with set notation? Okay, good. Wow, I'm shocked. Really? You guys didn't see this in your K-12 education? Wow, okay. I'm really shocked because I thought.
Did you have education high school in the US or in? Did you have high school education in the US or outside of the US?
Me in the U.S. I was born in North Carolina.
Oh. I know some friends from outside the US and they see this like.
Yeah, I would think so. Yeah. Yeah, I've lost my North Carolina accent, but I was born in North Carolina. If you don't mind me telling kind of an amusing story, I once, when I first started teaching at the University of Chicago as a graduate student, the administrator came to me and said, like early on in the term, she came to me and she said, "Winston, I have to tell you that a student came to me today and said that he had to drop out of your class because he couldn't understand your accent." And I was like, is it my North Carolina accent? Do I still have my North Carolina accent? I don't think I do. But she said no. She said, the student insisted that, she said, I told the student that she knew me and that I didn't have an accent, but the student insisted, no, he has a very strong Chinese accent. And he had to switch out of the class. So she let him. Yeah, but it's kind of amusing. Yeah, there are actually some, like psychological reasons that might happen. Like, there are some experiments where they show that people's minds influence what they hear, right? So they see this person, even though the person is dubbed over with an American accent, they hear the whatever accent they see, and vice versa. They take an American-looking person and dub it with a Chinese accent, and they don't hear an accent. So yeah, how the mind affects your hearing. Okay. So next thing, ordered sets. Ordered sets. So okay. So first thing, so you give a definition. So I always write definition like this. So let S be a set. Let S be a set, and this arrow be a binary truth relation on S. All that means is that it's something that takes in two elements and then gives you a true or false. Okay, just like your standard less than sign, right? You feed it two numbers and it'll say true or false, right? 5 less than 4, false, right? 4 less than 5, true. Okay, so it's just something that takes in two arguments and then returns true or false. Okay, so so let there be a set and a binary truth relation such that one, for every pair of elements x, y, in S, only one of x less than y, y less than x, or x equal y is true. Okay. So no matter, whenever you take two numbers, whenever you take two elements of the set, only one of these statements is true. Okay. And then 2, if x is less than y, y is less than z, then x is less than z. Okay, the transitive for x, y, and z in S, then this is, okay. So in that case, we call this thing an order on S. Okay, and we call the pair S with the relation an ordered set. Okay, so here's this abstract definition. It's basically just generalizing something that you're very familiar with. So for an example, the real numbers with the standard order is an ordered set. So this the standard order, right? So like if you have your standard less than or equal your standard less than sign, that's an order, right? Because it satisfies both of these properties, right? It satisfies this transitive property, and it also satisfies this condition that given two numbers, only one of these things is true. Okay. You could also use Q with the standard order. That also would be fine. Right. Here's kind of a non-example. Suppose you let S be all subsets of R2, say, and the order be containment. Okay. So is that an ordered set? Is that an ordered set? Does it satisfy both of these conditions? Let's look at the second condition, right? Suppose you've got three sets, A, B, and C, and A is contained in B, and B is contained in C. Is A contained in C? Yeah, right? So set inclusion satisfies this transitive property, right? But what about the first condition? Does set inclusion satisfy the first condition? Natalie says no, right? And no, it doesn't, right? Because you could have sets that are not equal to each other, but yet neither contains the other, right? You could have sets like this, right? They're not equal sets, but A is not contained in B and B is not contained in A, right? So this doesn't satisfy it's not well defined. Okay, so this is not an order. So this thing fails to be an order, and so the S with the inclusion is not an ordered set.
Well, can you re-explain again why one of that? Like so if you have that set,
Yeah.
with some elements of A not in B and vice versa, then for you pick every so A is not equal to Y for sure.
Yeah, they're not. So here's
but
your
like,
set.
none of that. Oh, so none of the conditions are true, right?
That's right. None of these is
okay.
true, right? But for inclusion to be an order, you'd have to have one of these things being true,
Okay.
right? But in fact, none of them are true.
Okay.
So you can easily create examples where none of these is true, and so it's not going to be an order. Okay. But you could you could consider the set of circles centered at the origin. Consider the set of circles centered at the origin with that inclusion as the order. Well, that would be an ordered set, right? Because the transitivity is still okay. And whenever you take two of these objects, one is contained in the other, or they're equal to each other, right? And so the set of circles, if we say, let S be the set of circles centered at the origin, circles centered at the origin with this inclusion, that actually is an ordered set. Okay. So just to show you that this idea is a little bit more flexible than just numbers and less than or equal. Okay. Okay. Sorry to keep you over. That's it for today. I went a bit slower than I would normally do because I wanted to show you guys how to think about formulas, right? Yeah. So yeah. Okay. Normally I'll go a bit faster.